linear regression. Linear regression is just a simple case of GLMs. Okay, that's clear. GLMs can be fitted via maximum likelihood. So if this can be done by maximum likelihood, we want to do the same with maximum likelihood, but not how it's normally done, but with convex optimization. And this is also one of the main key ideas. With the exponential cone optimization, we can involve constraints involving exponential functions. So one of the main drawbacks is like in general GLMs are fitted via so the standard technique to fit GLMs is using iterative reweighted least squares, and this procedure has some problems if you involve linear constraints and other constraints. So we will come to that later, but you might have seen this already if you fitted some GLMs in now. So what was our goal of this project? Was to use conic optimization to solve the maximum likelihood for fitting GLMs. And of course, we wanted to put everything together in a nice to use library for the R community. And one could also like now do the conic formulation, like do the tedious math of reformulating this as exponential optimization problem or as conic optimization problem, but this is probably not the interesting part of the talk, so I will skip that. So what constraints can you use for improving your models? We have worked on various constraints. So yeah, you can all see them on the page, which is global sparsity, group sparsity, modular expertise, bounded domains, linear constraints on in-out variables, and sign coherence constraints, and I will explain all of them. But let's come to the package first. So the package is called Holy GLM, and it's a package for fitting holistic generalist linear models, and it's already in Quan, so you can easily install it via Quan. And so one of the key features, its usage should be as simple as using the GLM function from stats, because that's a really nice function and many of us use it every day. And for modeling the underlying optimization problems, we use the ROI, the air optimization interface. And alternatively to ROI, we could have also used C4XR, but yeah, we were already comfortable with ROI, so why change? And so I will now go on with a small, I don't know, motivational example why I personally really like Holy GLM. So if you ever were using GLM in R, so it should be easy to use even when it's painful to use GLM. So if you ever were fitting some GLM in R, you might have stumbled across this. You're having your formula, and you have a data, and then you have your link and your family combination, and then R tells you no valid set of coefficients has been found. Please supply some starting values. And then you think to yourself, I don't know them. What should I do? And this is, in my perspective, a really pain point, because what I do then is type in 0, 0, 0, 0, 0 for every coefficient, and then it might work, but then sometimes it still might not work. And with Holy GLM, since we're not using iterative weighted least squares, but we're using convex optimization solvers as a backend, this does not happen anymore. So what we do, we simply switch the GLM function with the HGLM function, and now everything works nice and smoothly out of the box. It's the same formula, it's the same data set, it's the same family link combination, but we don't encounter this basic error where no starting values are needed. So this is one of my favorite things about it. And as one can see, if you provide the starting values, then it will converge to the same values with R, if you know the starting values. Yeah, okay. So for the optimization, we basically start with an optimization problem, and most of the time we have these big M constraints. which are integer constraints to either select covariates or deselect covariates. So if we go on, for example, I said we have a global sparsity constraint, and the global sparsity constraint is actually the classic best subset selection. So we want to select k coefficients such that we select at most k max coefficients, and the k max has to be chosen beforehand. So we can use our HGLM function, and now we have this additional constraints argument where we can, for example, specify this k max 2. So we want to select at most 2 coefficients in our model, and here we see it really only selects for the coefficient. It only selects 2 out of the 3 possible coefficients. So actually it maximizes the likelihood with this additional constraint in it. And we can also look at the active coefficients, and here we say, okay, the intercept is included, and 2 of the other covariates are included. Yeah, that's the global sparsity constraint. The group sparsity constraint is similar. It also is a sparsity constraint, but not for global sparsity, but for other group type of sparsity. For example, if we want to limit pairwise multicollinearity, or to select the best nonlinear transformation, or for example, for modeling splines. So here again, we want to have the sets in our constraints to be smaller or equal than a chosen A. For example, for the pairwise multicollinearity, we created here some data, and here we can say, we can see, okay, the x1 is highly correlated to the x2, and we can also see that the x3 is highly correlated to the x4. And here we fit now a whole GLM model for our data, and we put in 2 constraints. We can also combine the constraints via the classical R combine function. And we have here 2 constraints. One is the global sparsity constraints to select at most 3 covariates, and the other one is the pairwise multicollinearity, where we say, okay, if covariates are correlated, we want to select at most 1 of these highly correlated covariates about. So yeah, and for the result, we can really see, okay, for x1 and x2, only one of them is selected because they have a high correlation above this threshold, which is specified here, and the same also happens for x3 and x4. Yeah. We can also use this group sparsity to select the best nonlinear transformation. For example, here we model in the formula, okay, we want to have the distance from this data in the formula, and also the logarithm of the distance, and the same with the pop and the logarithm of the pop. And here we say, okay, we want to have a group sparsity of these 2, and we want to select at most 1 of these 2, and the same for the other variable. And as we can see in the result, again, the model only selects 1. So it selects only the 1 for achieving the maximum likelihood. Yeah. Another constraint is the model expertise. So we can force the inclusion of a covariate because the modeler is always right. This is often a business case thing where you are forced to include something into your model. And for example, we have the example from before where we only where we have this sparsity constraint again. And if we remember before, risk and untip were selected, but this time we forced the inclusion of n-plan, and of course it's now in the model. We can also use this to bound the domains for the covariates. Some use cases for this would be non-negative regression, which can have some regularization effects similar to lasso, or if we know about physical limitations of the covariates, or yeah, just if we want to put some bounds on the coefficients of our covariates, we can specify them here with a lower and the upper. So for example, here we specify as bounds, lower bounds for risk and untip, and upper bound for M-plan. And as we can see, a model is again built which satisfies this constraint. The next constraint would be the sign coherence constraint. So what the problem is about pairwise multicollinearity is this canceling effect. So what you have, if you have highly correlated coefficients, what happens is that sometimes both are included, and if they have a negative, if they have opposite signs, if the coefficients of the covariates have opposite signs, then they're canceling out each other, and then these coefficients might be higher than they actually have to be, like the absolute values push themselves higher than they actually need to be because they are canceling each other out. And with this sign coherence constraint, you can enforce the signs of the coefficients to be on the same page. So they either have to be positive both, or either both have to be negative. So that you don't experience this canceling out effects. And yeah, of course, we can see this is happening for the location. And so if we look at the coefficients of location diff for south, north, and west, we can see they have the same. We can see they have the same sign, and the same happens for the location north, location south pop, and location west pop. The same happens for the organ. Yeah. We can also put linear constraints on our coefficients. So we can say that we want one coefficient to be smaller, equal, or less than equal than another coefficient, which happens here. Yeah. Or we can say that the sum shouldn't be above something, just putting linear constraints on the covariates. Or we can also put linear constraints on the set variables, where the set variables are the variables which are the selective variables of these coefficients. So this is, for example, useful if you're modeling something with polynomials or splines, and then you only want to include a higher degree, for example, or if you include a higher degree, you also want to have the lower degrees included, for example, where we have here our polynomial case, and here we enforce the inclusion of the lower polynomials because we already selected the higher one, and the higher is much more expensive to select, for example. We can also use the package for estimating a sequence of models. So for example, if you want to do this best subset selection, as we said beforehand, you have to specify this Kmax before, and maybe you want to do this for all possible values of Kmax. So for 1 up to the number of covariates, then you can use this HGLM seg function for this, for calculating all these possible models, and you can also plot them. And here in the plot, you can for example see the ARC and the BRC, and you can also see how these coefficients might shift in or out. So if you want to do some model selection and you want to see how stable are the coefficients staying inside your model, you can use this plot for seeing how stable they are in the model or not, and this might help you for your model selection. For example, you want to choose a model with the lowest AIC, then you might choose one of around K8 or 9 here. And so how is the estimation done for this package? As I said before, normally GLMs are typically estimated via iterative reweighted least squares, and we do this not with iterative reweighted least squares, but with conic optimization. For most models, iterative reweighted least squares is faster, but for certain GLMs, e.g. the log binomial case, conic optimization is faster. We also saw the case where we need starting values for the iterative reweighted least squares, and conic optimization does not need this. And there's also the fact or saying that iterative reweighted least squares sometimes fails to converge. And most conic basically all conic optimization solvers provide optimality certificates, so you can really be sure that you have the best model, so to say. And our package supports, as we said, we have an optimization. There's an optimization model which is solved behind this, and we basically support a various number of different optimization solvers, depending on which licenses you do own and which you do not know, which you don't own. And there are a lot also of open source solvers which you can use, at least enough. Yeah, so that's it. Are there any questions?
So, thank you, Benjamin, for your interesting talk. I'm asking the audience for any questions so far. Yes, please. Well. So, you present this sequence function.
Yes.
With this wonderful plot of DSC values.
Yeah, the colors are awful. What? The colors of the plot are awful.
No, so they give you a hint of which where the best policy is for. But on the other hand, I just started out with the default call of the GLM, which gives you some result where supposedly GLM will give you a result because you're not providing for the values. Now, you have talked a lot about different constraints that you may apply to your problem. But what would be, your motivation of putting these constraints in the first place, and how would you compare that to, say, the default solution that is provided by not providing a constraint?
So I think the basic motivation is probably the global sparsity constraint, which because the idea is the basic idea is that if you have a sparser model, it becomes more interpretable, and it might be faster to predict also, because of course the matrix multiplication gets smaller. But yeah, I think it becomes more interpretable. If you say, okay, I have this, I don't know, 70 covariates, and I don't know which of them are how important. And if I say I want a model with only 10 covariates, because that's things I can grasp.
So that's sort of an advanced step procedure that you know.
Yeah.
The next step would be to go more into the direction of
automatic machine learning. Yeah. So this would be, and we are currently working on this step for using for making this more, for automating this even more.
So, for example, this constraints on the collinearity of factors. So that seems quite interesting, because usually we'll have to pay attention to that. So if you have a chance of limiting these effects of the magic slide, of course.
Yeah.
But the other hand, the question is how much information you learn if you solve some of these.
That's a really interesting question, because we had to think a lot about this, and at first we started with always including this multi-collinearity constraint, that we want to exclude multi-collinearity covariates. But then the question arises, where do you set the threshold? What's a good standard value for this? And the question also is what is really like I don't know, kind of painful, or you start to diverge basically if you do it as a default. If you always include this constraint by default, then you basically diverge from the GLM function, and that's not something you want to do in the first place, because people might get really surprised if the models from the GLM function and our function might diverge in the first place, even without them specifying constraints. So if you want to do automatic model selection, I would definitely include it, but this should be more seen as a toolbox for the modeler right now. And the next step is to package everything we learn from this process into a more sophisticated automatic model selection.
Okay, that's good. Thank you.
And then for the collinearity constraint, you have also this nice equal sign collinearity. And there are things most likely get easier to choose the value for the correlation, because in essence you can choose a lower value, just not this rule of thumb, this 0.8, but because actually also there's the question to normally model this by hand. So where if you look at the correlation, that will cut. So what one can do if one is, of course, this being Lasso, and then Lasso will randomly drop one of the coefficients, highly correlated, and then you learn in some sense here this L1 penalty, how far it can regularize, not how far I can drop this stuff. But this equal sign constraint, I think it gets a little bit easier, because then it can stay in the model, but it's just forced to have a.
If not, I say thank you. Thank you for your talk. And we hope to do this every month. So this was the starting point, and I hope there's many more R meetups. In any case, we are always searching for speakers. So yes, we'll find somebody. And in any case, we're heading now, I guess, to some nice restaurant. Stay tuned and see you next month.